Hello.
Hello.
Yes, sir.
Yeah. So can you hear me? Actually, there was network issue, and then I was
Yeah.
disconnected. Yeah. Yeah.
Yeah, sir.
Tell
I'm
me.
getting 5.97, sir.
Acha. So it is. Yeah. So it came right.
PI.
5.97.
Yeah, right only. PI is equal to 9.
Yeah. So now we will move on to.
Sir, slides not visible.
Can you now show the? Can you now see the slides?
Yes,
Discuss.
sir.
Okay. Okay. Fine. Yeah. Yeah. So in glycine you have cross checked, right? That pi what you were calculating, that is pk1 plus pk2 by 2, right? Is it matching?
Yes, sir. It is matching.
Okay. So now we will go to a complex
Then,
and
sir,
yes, yes.
how we will know about the PK1 and PK2 value?
pk1
That is
that are
2.35.
actually given in textbooks also. Whatever textbook you follow, you can get it. And so this is a formula actually.
Okay, sir.
So
So we have to remember those all PK1 and PK2
yes,
value.
yes. Please note it down because in your exam it may come that they will give PK1 and PK2, and then you might be asked to find the PI. Okay. So for that you can use that formula. So please note it down.
Yes, sir.
Okay. So next, so uh, you are Pranam, right? Or am I making any mistake?
Yes, I am Pranav.
Okay, okay, fine.
Pranav.
Okay.
Yes.
So now we will go to glutamate. So glutamate is what kind of a amino acid? Aditya, which class glutamate belong to? Yeah. So glutamate actually belongs from polar negative charge amino acids, right? Because it has two carboxylic acid group. So now we will see uh, what happens during the titration of glutamate. So initially glutamate exists at as this form, right? Then as we keep adding OH minus, then glutam- glutamate will lose its first most acidic electron. Uh, proton, right? So here this is the most acidic bond, right? So when we add OH minus, then they will take out this proton. So it will become C double O minus, right? So initially it has charge plus 1. After elimination of this hydrogen, it has charge of plus 1 minus 1 equals to 0. That means it is existing in deuterionic form, right? And at the pH equal to pK1 of 2.19, it will exist as equal amount of this deuterionic form and this form. Then again, when you will keep adding H minus, then what will happen? Then the next acidic hydrogen will be removed, which is this one, right? So next acidic hydrogen will be removed and there will be a negative charge here. So now it will exist as NH3 plus CO minus CO minus.
Yes.
That means at minus charge, total charge is minus. So here it was, so if I use something, just a minute. Yeah. So here the charge was plus 1. After losing this, it will exist as zero charge form.
Deuter.
Deuterionic.
Deuterionic form.
Very good. And then it will lose this proton. So now it will become minus 1.
-1.
Yes. Right. And at the pH equal to pKr, which is 4.25, pH equal to pKr, this molecule will exist as equal amount of this deuterionic form, this minus 1 form, and
Yes, sir.
and then it will remove this proton from this NH3 group, right? So now it will becoming NH2. So now it has minus 2 charge, right? So at the pH equal to pK2, which is 9.67, it will exist at equimolar concentration of this minus 2 form and minus 1 form, right? So now if I will ask you that what is how much is the Pi for this, then how will you calculate? For glycine, here it was plus, then losing this it became 0, then losing this it became minus 1, right? And from always remember, when you will shift from plus 1 to minus 1, right, then in the shifting plus 1 to minus 1, and if there is a 0 in between of them, then Pi will be equal to pK1 plus pK2 by 2. But for here, as it has a side chain is acidic, right, so that's why it had a pK1, which is for this COOH, pKr, that is for side chain, right, for this H, that is pKr, and pK2 is for this amino group, right? So pK1 pK2 is there, but extra is pKr. pK1 pK2 was also there in the case of glycine, but here along with the pK1 and pK2 it has pKr, because it has a acidic hydrogen in the side chain. That's why it is pKr, right? So now for this case, the Pi will be, if I will ask you to calculate the Pi, then Pi will be, again see,
PK1 plus PKr plus PK3 by PK2 by 2.
No. Anyone else? Always check the Pi. Pi is at the pH where the molecule will exist as the deuterionic form or zero charge form, right? So for this, for example, glycine, you will always check this plus 1 to minus 1 transition, right? If the Pi is between plus 1 to minus 1, then your Pi will be pK1 plus pK2 by 2. For here, if you will see the transition from plus 1 to minus 1, this is like this, right? So between pK1 and pKr there is Pi or zero form, right? Between pKi and pKr there is zero charge form or deuterionic form. So now for this case, Pi will be pK1 plus pKr by 2. Okay. So now you please tell me what will be the Pi for this case? Pranab, you understood?
Yes, sir.
So always check this transition plus 1 to minus 1. If your deuterionic form in between or zero charge form is in between plus 1 to minus 1, then Pi will be pK1 and pK1 plus pKr by 2, right?
Sir, so why we are not taking -2?
Yeah, very good question. Because your deuterionic form is lying between this pk1 and pk2. Okay, sorry, pk1 and pkr.
Oh, yeah.
Right, so that's why the pi will be the average of the this preceding pi, I mean the
Yes, sir.
preceding pk and the following pk. Always check for this transition +1 to -1. So for this
Okay.
case, what will be the pi?
PK1 plus PKR by 2.
Uh,
2.19 plus 4.25 by 2.
yes, very good. Okay, so that will be the pi. So now let's study the histidine. Histidine is polar positive charge amino acid, right? So, so initially it will exist as +2 charge from. Okay, see, +2 because it has one plus charge here and one plus charge in the side chain, right? So that's why this. Okay, so that's why this hydrogen is acidic hydrogen. So in the first step, when we keep adding base, then at the first step, what will happen? This hydrogen will be removed, right? So now it will be exist as from COOH it will become COO minus. So the charge is plus -1 plus 1. So plus 1, right? Again we will keep adding the base. Then what will happen? This positive charge over the side chain will be removed, right? See, from NH it has become N, right? So that's why it is pKr. So now this is a zero charge form or neutral ionic form. So here charge is 0. And then if we keep adding the base, then what will happen? Here this proton will be removed. So NH3 plus will become NH2. So now it has -1 charge, right? So now you tell me what is the pi for this case histidine, or the formula in histidine. How will you decide?
PKR plus PK2 by 2.
Very good. So it is +1 to -1. So right. So 0 is falling between +1 to -1, means between pKr and pk2. So the pi will be pKr plus pk2 by 2. So any doubt? Anyone?
Hello, sir.
Yes. Any doubt?
Can't. No, sir. Can't see your screen.
Okay, okay. Okay, just
Sir, if any friend, my friend, want to join, they can join.
I think there
Yes, sir.
is the rule of registration, the
Yeah, yeah.
ISS, and this form will
If it is it is open, then they can join.
that I don't know actually. If you, that for that you need to contact IQPS. They will.
Actually, sir, I also applied for one molecular techniques that is for Rishabh sir is there. I don't know, he's from maybe Kharagpur. So maybe I was one day late. Then I did not get any link of the class. Registration is open, but I did not get any link. I also mailed them IAS, but I did not get any reply.
Yeah, but actually for the, I mean, I don't have the authority for this, so you have to really contact with
Okay, sir. Sir, in this course, we'll get certificate also, like.
you please confirm these things with
Okay, sir.
yes,
Okay.
because we are only here for teaching.
Teach. Yeah.
So I hope the slides are visible right now. Okay.
Yes, sir.
Yeah. So now we will shift to protein structure, right? So we studied the amino acids, its titration, its composition, its classes, and then we will shift to protein, right? Proteins are made up of amino acids, as we know that in the primary structure is nothing but the series of amino acids which are joined together by peptide bonds, right? And from this primary structure, when they have a shape, for example alpha helix or beta sheet, they are called secondary structure. And then more, yeah, so after that when this secondary structure will come together and take a further shape, that is called tertiary structure. And then quaternary structure is when one or more than tertiary structural peptide chains are coming and they are getting assembled, and right, so they are quaternary structure. Suppose the proteins, if a protein is multiple subunit, it has multiple subunit, then each subunit is coming from they have a tertiary structure, and this different polypeptide chain will come and assemble and they will make a quaternary structure, right? For example, hemoglobin, it has four subunits: alpha 1, alpha 2, beta 1, beta 2. So that's why hemoglobin has a quaternary structure. But for myoglobin has only one subunit, so it has tertiary structure. Okay. So these are the level of structures in proteins. So then if you want to go to the protein purification, how will you purify a protein? Achha, why do you need to purify protein? Suppose you have a
Sir.
cell and you are lysing the cell and you are getting the cell lysate. So from that, why do you need to purify the proteins? Somebody is saying something? Please go ahead.
Sir, can you explain that alpha helix and beta plated seed of the protein?
Yes, that we will anyway discuss in details. What is alpha helix and beta sheet. So here I wanted to say you when the primary structures that will uh, take a shape, and that can be achieved by intermolecular interaction. For example, this lysine can interact with histidine, right? So this intermolecular interaction, and those interactions are van der Waals, hydrophobic, hydrogen bonds, electrostatic interaction. So when these kind of intermolecular interactions will happen, then the intermolecular means in this molecule there are many amino acids. So intermolecular means within the molecule. So within this within this polypeptide chain, when these amino acids are uh, interacting with each other, right, and then they are taking a shape. That shape is called secondary structure. And the examples of secondary structures are alpha helix, beta sheet, beta tart, that we will discuss in detail, right? So, and this each secondary structure, see, for example, this alpha helix is shown here. So, when this each of the secondary structure, this alpha helix, uh, they are coming together and they are taking a further complex shape that is called tertiary structure. And then one or more the tertiary structures are coming and they are getting assembled, then this is called quaternary structure. So now you understood the
Yes,
basics?
sir. Sir, this is basic. You will explain this all.
Yeah, yeah,
Okay.
yeah. So I was asking, why do you need to purify proteins? What is the need of this? Suppose a cell is expressing protein, so now why do you need to purify?
some contaminations would have to be there, like protein with some enzymes. So we need to purify them.
Yes, kind of. Yes, you are close. So when you are lysing a cell in the cell lysate, there are of course other proteins are there as you were saying, correct? That other protein will be there, but along with that it will have carbohydrate, it will have lipid, it will have fat, right?
Yeah.
So yeah, so everything will be there. So you are and you want only the protein. So that's why you need to purify the protein, right, from this entire pool of cell lysate. So the first technique we will discuss is ion exchange chromatography. Chromatography, anyone knows? Anyone can tell me in, briefly what is chromatography?
So basically, chromatography is a technique to separate, purify component
Yes, very good. So in chromatography, there is
based
a
on the interaction.
yes, that is a key point. That when the samples are loaded into a stationary phase, then due to of some interaction, it might be right. Sometimes it is interaction, sometimes it is about the size, right? So how fast a molecule can travel or not travel through this stationary phase. If a molecule has interaction with this stationary phase, then it will be trapped, right? So in this way you can purify the proteins, right? I mean, you can separate. Some proteins will take slow time, more time to travel. Some protein will take less time to travel. Some protein will have affinity, some protein will not have affinity, right? So that's how we can purify the proteins. So you are right, correct. So the first thing we will discuss is ion exchange chromatography, right? So here the stationary phase are the polymer bits with a negatively charged functional group, right? So the stationary phase is negative charge. Now you are pouring one cell lysate where proteins will negative charge, positive charge, right? So mixture of all of them. So now when you will pour, then what will happen for the negative charge protein? For that, when you will pour, can will they be will they interact with the bead? If your stationary phase is negative and and you are loading the negative charge protein, so can they interact?
Yes.
How can they interact? They should not interact, no? Because they have negative charge.
Yes,
There,
sir. Both have.
so there will be repulsion, right? Negative, negative repulsion.
Yeah. Yeah.
Yeah, so
So,
they will not interact with the stationary phase, so they will come out, right? So first they will come out, but the proteins which has the positive charge, they will interact, right? Because of this positive negative interaction, so they will be trapped,
yes.
right? Now,
Yes. Yes.
yes. So now, in order to elude them, you need to add, for example, you can add NaCl. NaCl has Na plus, right? So now Na plus will interact with this bead and it will replace the bound proteins. So the bound proteins will be eluded, right? So in the washing step, the proteins which has uh, negative charge, they will come out, right? And the positive charge will be trapped. But now in order to elude the positive charge protein, you will add NaCl. So NaCl has Na plus. So Na plus will replace the positive charge protein and the positive charge proteins will come out, right? So that is the idea of ion exchange chromatography. Next is size exclusion chromatography or gel filtration and gel filtration chromatography, right? So here uh, the stationary phase is filled with uh, the beads which has porous size. Okay, so now this cell lysate which you are pouring here, that is either a small size protein or large size protein. So the small size protein that will enter into all of the pores, and it will take more time to travel this, right? Why? Because it will enter into each of the pores. So that's why its path length will be increased. So it will take more time to be eluted. And the proteins with higher molecular weight, bigger proteins, they have the lesser path length because of their size they cannot enter into this bead, right? As they cannot enter into this bead, so they will just bypass the bead, right? So for their case the path length will be shortened. So they will first, so the high molecular weight or larger molecules will pass more freely. So first they will come, and after that the smaller molecules will come. Okay, so that is gel filtration chromatography, where you can differentiate along based on the size. Right. The next is what you were saying, that affinity chromatography. Right. Here the stationary phase is filled out by the ligand with which one of the protein is bound. Right. For example, antigen antibody. Right. Do you know about antigen antibody, Pranab?
Yes, is present on bloods.
Can you repeat? I didn't get your point actually. Hello.
Sir, antigen means a foreign substance like of protein, polysaccharide that triggers the immune response.
Yes, and antigen it antigen binds with what? Interacts with
Antibody.
antibody. So if you want to purify,
Yeah.
suppose suppose you are given with a mixture of multiple antibodies, right? And now you want to purify a specific antibody. For example, uh, you have antibodies from different patients of suppose, as in the COVID time, we had multiple strains of SARS-CoV-2, right? Am I right?
Yes.
Yes,
Yes.
yes, multiple strains of SARS-CoV-2 were there. So now you have a mixture where you have the antibodies from the patient which who were infected with that different strains of the SARS-CoV-2 COVID. Okay, but you want to purify the antibodies which is for uh, one of the Omicron strain, right? Omicron, you know, right? Third wave which came. Yeah. So
Yes.
yeah. So suppose you want to purify the Omicron antibody among all other antibodies. So how will you do? You will make a stationary phase, right? In stationary phase, you will fill the bit with antigen, right? Which has,
And
yes, which has the antigen for,
antibody.
yes, which has the antigen for that specific antibody, right?
Antibody.
Yeah. So now you have here mixture of antibodies. So when you will pour, only that specific antibody will be attached, will be trapped. Other antibodies will be passed, right? Other antibodies will be washed. So only the specific antibody will be trapped here, and later you can elute that specific antibody by using elution solution, right? Then you can collect your specific uh, antibody, right, by using this antigen antibody interaction. So these are the three processes of protein purification we saw, and next we will see the some techniques of which is electrophoresis. I think you have heard about that. That this is made up of a gel, SDS pen gel, right? So in this gel, there will be different wells, so we can load your samples, and then you will pass an electric field, and the samples will be negative charge because you will add SDS to the sample, and SDS imparts a negative charge to the proteins. So when you will initiate the electric field, then from negative to positive direction, the proteins will start migrating, right? And the higher molecular weight protein will migrate lesser, and the lower molecular weight proteins will migrate more distance, right?
More, more.
Yeah, more, correct. That's why you can uh, separate the proteins in your mixture of proteins because according to their molecular weight. Here, as you see, they have been separated. Myosin has different molecular weight, ovalbumin has different molecular weight, and you can also calculate molecular weight of an unknown protein, right? Because if you will plot a standard carb by using some known protein and their migration, and you are plotting migration in the y-axis, migration in the x-axis and molecular weight, log of molecular weight in the y-axis, then if you can plot a standard graph, right, by using some known proteins, and then if you have an unknown protein whose molecular weight you don't know, then you will calculate the migration. This is the migration. So by using this curve, you can know the molecular weight, log of molecular weight of that particular protein. So that's why you can determine the molecular weight of an unknown protein by using uh, gel electrophoresis. Any doubt? Please ask me.
No, sir.
Oh, thanks. Okay, so we are done with the technique. So now we will shift to the secondary structure, which I told you here, that this secondary structure. So now we will go to that portion. So before that, before starting that, I would like to inform you that secondary structure is the first you clear this concept. The secondary structure is a intermolecular structure, right? Suppose, for example, suppose there is a polypeptide chain, right? There are different antibody here. Antibody, different amino acid one, amino acid two, right? Three, and then seven, right? So intermolecular interaction means suppose this number two is suppose aspartate, right? Aspartate has a negative charge, and aspartate is denoted as D, right? Always remember all of the form of this amino acids. Yeah.
Single
Suppose this
letter code for amino acid.
the letter code. So suppose in two position you have D, and at seven position you have E. Sorry, in seven position you have H, histidine, right? So it is positive charge, it is negative charge, right? So now this 2 and 7 has opposite charge, so they can make a interaction which is ionic interaction, plus minus. So now this polypeptide chain will take a shape. This is your 1, this is your 2, right? So this will bend, right? Bend like this 7, right? So that 2 and 7 will come to close proximity as their opposite charge, right? 2 has a negative, 7 has positive. So they came to close proximity, and 3, 4, 5, 6 are there, right? So this kind of structure, intermolecular structure, based on the interaction between the intermolecular amino acids, this structure is called secondary structure, right? So, yeah. So before starting that, we know that in a polypeptide chain, for example here, this polypeptide chain, which is the primary structure, The amino acids are linked by the peptide bond, right? Now, peptide bond is rigid. Why rigid? Because this is one amino acid which has a R group, which has the N terminus, which has the C terminus, right? Right. This is C and this is O. This is N. This is R group, right? So, and this is the amino terminal of the next amino acid. This is the C alpha, and this is your carboxyl terminal of the next amino acid, right? So this is the bond which is peptide bond. C double O NH. C double O of previous amino acid and NH of next amino acid. This bond is called peptide bond, and this bond is rigid because this bond is planar, right? That's why because of this planar because of this planar property, this bond cannot rotate. So it is rigid. That is called rigidity of peptide bond. So which bonds can rotate? For example, suppose this C alpha and between this C alpha and this C alpha. So which bond can rotate? This NC alpha bond between C alpha and the N terminus. This bond, right? And C alpha and C terminus, right? This C terminus and this C alpha, this bond can rotate. After that, this is your peptide bond. So this is rigid, right? This is rigid, so it cannot rotate. But this bond and this bond can rotate, right? So there are two terms. There are two dihedral angle when one is phi and one is psi. Phi is the dihedral angle that is measured upon rotation of this C alpha N bond, right? Right, and the psi angle which is measured according to the rotation of this C alpha C bond, right? Based on this different value of psi and phi, this polypeptide chain can this amino acid can take different conformation, right? That is called rigidity of the peptide bond, and these are the dihedral angle. Next, Ramachandran plot, that is depending on the phi and psi angles, right? So there are some regions. These blue regions are the stoichiometrical allowed region, right? If your phi and psi, suppose for this region, psi is 120 and phi is around 80, right? So this portion is in allowed region. So in a protein, phi and psi combination can be there to exist a stable form conformation of a protein, right? So Ramachandran plot tells us the range of psi and phi value, right, where the protein can take a stable conformation. Any doubt here?
Sir,
Yes. Yes.
sir, these Ramachandran plots for the secondary structure of the protein.
Yeah, that I will show you. Ramachandran plot will actually tell you that what are the allowed combination of phi and psi. Okay. Then we will
Yes,
see
sir.
that what are the allowed
Sir,
What?
this
Yes, yes.
phi and psi value is just this all are the rotation only, no?
Yes, rotation phi is rotation of C alpha C. So, rotation of those two bonds which are not rigid. So in this space is 360 degree, right? So in this 360 degree range, it can take any conformation, right? So based on that, but all of the conformation, for example, this region, if you are suppose in this region, phi is how much? Phi is suppose 90. Sorry, phi is suppose minus 90. Sorry. Phi is suppose 120 and psi is suppose minus 90. Right. So this region is not allowed. If amino acid is uh, having this conformation, then that amino acid will not be stable. But if amino acid have this combination, uh, for example, psi equal to minus 90 and phi equal to minus 90 and psi equal to 120, right? Right. So that that combination is stable. That combination makes amino acid stable. Understood?
Like,
Huh.
sir, uh, phi phi will be 90 and
Phi will be
psi will be uh,
if phi is 90, okay, fine then psi
psi will be 120.
no, then it will be not be stable.
It's not really stable. If phi will be minus 90 and psi
Phi
will
will
be
be
120, then
wait. Phi will be minus 90.
minus 90.
Minus 90 means here, okay, and psi
Psi will be 120.
120. Huh. Then you are falling in the allowed region. So that confirmation
Is
is allowed
stable.
for stability. Understood? How to use this plot?
Based on the phi and psi value.
Yes, based on the phi and psi. Very good. Okay. So others, if you have any doubt, please ask me. So this is specific for alanine. Okay. So for different amino acids, you will have different Ramachandran plot.
Plots.
Yes, very good. So for alanine, these are the phi and psi combination which will make this amino acid stable. Right? And these are the combination which will not make amino acid stable. These for alanine. For each amino acid, you will get different plot. These for this alanine. So next we'll move to one of the secondary structure which is alpha helix. Right? Helix. What is helix? Define me helix. What is helix? Or helical structure you say. What is that?
Sir, helix is a spiral substructure.
Spiral?
A spiral substructure.
Spiral shape, okay.
Yes, sir.
Okay. So DNA you have
The
studied
DNA
double
have
helix.
helix.
DNA you have studied, right? It has a double helical
Yeah,
structure.
double helix. Yes.
Yes. But in alpha helix for protein, alpha helix has single helical. Okay, single
Yes,
helical.
sir. Made up of hydrogen bonding.
Hydrogen bonding, very good. Right? So for example, here you can see that these amino acids are forming a helical shape, right? So if you see the backbone, this is a S kind of helical shape. Okay. So as I told you that how these intermolecular structures are achieved by interaction. Similarly here, this amino acid, the CO group oxygen is interacting with the, suppose this is your nth amino acid, then it will interact with n plus fourth amino acid, right? So if it is third amino acid, then it will interact with seventh amino acid. So CO group of third amino acid will interact with NH group of seventh amino acid. That's why this bending will be occurred. Similarly, this suppose this CO group of 11th amino acid will interact with NH group of 15th amino acid. That's why this bend is happened, right? So that's why these molecules take a shape of helix, helical bend, right? This is called alpha helix. It has, and in alpha helix, if you will see, this is a helix. So each of, so it is made up of some loops, right? So this is one loop, this is second loop, this is third loop. Okay, so in each loop there will be, so for in each loop there will be 3.6 amino acid residues, and this length is called as helical pitch, right? Right, in each loop the length so yeah, so in each loop the helical rise is known as the helical pitch, right? So per each loop there is 3.6 residues and the length is 5.5. Okay. So for the alpha helix, the so for the alpha helix, the informations are that in each loop there is 3.6 number of and the helical pitch, this rise per each loop is 5.5
Sir, helical pitch means the length.
length of each loop. Okay. So suppose, so after that, if I will give you a question that one alpha helix has the total
Three.
length of 54 angstrom. Okay. An alpha helix
Okay.
has total length of 54 angstrom. Right. So how many loops are there? Can you calculate?
36.
No, one alpha helix has total length of 54 angstrom. So how many loops are there? How many loops are there? How many loops are there?
'56 angstrom.
54 angstrom. And this information you know that helical pitch is 5.4 angstrom. So what are the number of, how many loops are there? Helical loops. Come on, it's easy. 5. If the total length is 54 angstrom, right, then how many loops are there? Each loop has length of 5.4 angstrom. Then in 54 angstrom, how many loops are there?
10 loops.
Very good, 10 loops. 54 divided by 5.4. And the next question is, in this 54 angstrom length, how many residues are there?
36.
How many?
36.
Yes, very good. 36. 36 residues are there. Correct. Okay, so answer is clear. And there is a term called helix dipole because in alpha helix one end is amino terminus and one end is C terminus, right? So amino terminus is positive charge and C terminus is negative charge. So there is an electric field between, right, between, because there is charge difference. So in this direction there will be electric field, right? So that is called helix dipole. So next section we will read is beta sheet, right? In beta sheet what happens? There are two kinds of beta sheets, anti-parallel and parallel. So in anti-parallel beta sheet, what so yeah, so here in the first layer is from N to C, right? But in the second layer is from C to N. This is NH, this is C double O, but this is C double O and this is NH. So N to C, if we consider this as a direction N to C, then the first layer has this direction, but the second layer has this direction because N is here, C is here. But the first layer, N is here, C is here, right? So that's why it is anti-parallel beta sheet, and interactions are right here. Here are the interactions. How? Between C double O and NH. C double O and NH. This is called anti-parallel beta sheet. Parallel beta sheet means the first layer has N here, C here, so this direction. Second layer also has N here and C here. Third layer also has N and C. Right? So again the interaction between C double O and NH. C double O and NH. Right? So here interactions are parallel here for anti-parallel, but for parallel interactions are not parallel. They are tilt. Right? So these are the two different kinds of beta sheet. Okay. So any doubt between alpha helix and beta sheet, quickly ask me.
Sir, little bit explain about this parallel and anti-parallel.
So you wanted to once more?
This parallel and anti-parallel. How to? What is
Series figure.
happening?
The first layer. This is your N side, right?
Yes,
This
sir.
is your N side. This is your C side. Right? So direction is in this direction, left to right. The second layer, N here, and carboxylic terminus is here. Right? So the direction is in this side. Okay? That's why it is anti-parallel. Okay? And interactions are
Yes.
happening in such a way that NH of first layer is interacting with CO of second layer by hydrogen bond. Right? Here, CO of first layer is interacting with NH of second layer. Again, NH of second layer is interacting with CO of NH of first layer is interacting with CO of second layer by hydrogen bond. Right? This is anti-parallel beta sheets, and these strands are close together by this hydrogen bond. Right? So now you understood why is it anti-parallel?
Yes, sir.
Okay. So can you explain me the parallel one? You want to try? Tell me. In the first layer, what is happening in the parallel? This is which side, N or C? This is N, okay? NH3. This is N and this red one is oxygen. Means this is C side. So this is N side. See, this is C double one O, right? That means it is C side. In the second layer, which one is N side? Pranab?
Sir, the The N terminus of one strand aligns with the C terminus of another. That is a parallel orientation.
Where? In parallel or anti-parallel? Where?
The NC beta C alignment of N terminus to the C terminus
In anti-parallel.
in parallel.
Parallel what's happening?
The alignment of N terminus to C terminus.
Okay, this is for first layer. For second layer, this is which side, N or C?
Just opposite. Just opposite.
Opposite means
The C terminus elements of the C terminus to the N terminus.
this is, that's why it is parallel now. N terminus.
Yeah.
Yeah, this is N.
N to C terminus.
Yes.
Yeah.
So parallel, same direction. Okay, and the interactions are between NH of first layer is interacting with CO of second layer.
Yes, sir.
Got it?
Yes, sir. Yes, sir.
Okay. Any doubt? So can you explain me the anti-parallel? What is happening here in anti-parallel?
The N terminus is N to C and C to N.
C to N. Very good.
No, sir. But the direction is N to C and N to C.
N to C, if we right, but in the second layer, the direction is C to N. See? Right. So in the first direction, it is like this.
Sir, in yeah.
And the second.
But sir, but the arrow is like N to C. Arrow, like arrow.
Arrow is always N to C, right?
Okay.
But the direction of the arrows. In the first layer, the direction is left to right. In the second layer, the direction is right to left. है ना?
Yeah.
This is in, this is C, this is in.
This is N, this is C.
This is
C.
Very good. Okay, so that's why this is anti-parallel. But for this case, parallel, all of the arrows are in same direction, left to right. NC, NC, NC. Okay. Okay, so next we will go to beta turn. Beta turn is they will connect to alpha helix or to beta sheet, right? So, for example, here these 4 amino acid residues are beta turn. They are connecting to two beta sheets. For here, this is parallel, this is anti-parallel, but in beach mein, in this middle, there should be someone which will bend, right? Then only this structure, then only this sheet will be formed. So this portion is called as beta turn. Okay. Here also. Here.
The beta turn.
Yeah.
Yeah.
They will the
Expression both parallel and
they
anti-parallel.
are the connecting element. They will connect.
They
They are made up of amino acid residues. Interaction happens because of this bending that happens between ionic interaction between hydrogen bond between 1 and 4.
Sir, can you show me the previous slides? Just want to see it. Sir, previous slide, can you show me for a few seconds? Yes. They will get this notes also.
That I don't know, but yeah, but I can send you guys by email.
Mail. Yeah.
Any doubt, you can ask me if you have any doubt here.
Yes.
Clear?
Yes, sir.
नहीं है कोई एग्जाम so as I told you these two beta sheets will be joined by beta turn. Okay, private beta turn. So this beta turn is made up of 4 amino acids. Okay, one, two, three, four. 4 amino acids, and uh, the interaction occurs between first and fourth amino acid. CO group of first amino acid and NH group of fourth amino acid. That's how this beta turn will be formed, right? And in the type 2, the only difference is the third amino acid will be glycine, right? Glycine means there is no side chain. So there are two types of beta turn. One is type 1, type 2. The difference is in type 2, the third amino acids will be glycine. Otherwise, the interaction will be always between first and fourth amino acid residue. If it is N, then this amino acid will interact with N plus fourth amino acid residue in beta turn. Okay. So this is the Ramachandran plot for secondary structures. As you can see that here in this region anti-parallel beta sheets fall, this region parallel beta sheets fall, right? Right-handed alpha helix fall in this region, left-handed alpha helix fall in this region, right? So there are different region for each different uh, secondary structure, right? And notice that all of the secondary structures are falling in allowed region, in the blue region. None of them are falling in the not allowed region, right?
Sir, in type 2 glycine is there. So interaction is the 1 to 4 amino acid.
Interaction will be always 1 to 4. Always. Right?
Yeah.
The other difference is in the type 2 glycine will be the third residue. Remember it. Okay, so this you understood that each of the amino acids, each of the secondary structure you will see that
Glycine will be?
Glycine will be the third amino acid here. Beta 1, 2, 3, 4, right? Here third will be the glycine. Understood? In type 2. Okay. अच्छा एक नंबर अच्छा प्राइवेट किया व्यक्तिगत
Yes, sir, understand.
हाँ So now the Ramachandran plot for secondary structure, as I told you, that each of the secondary structures are falling into the allowed region of the phi-psi combination of Ramachandran plot. See everything. Anti-parallel, alpha helix, right-handed alpha helix, left-handed, parallel beta sheets, all are in the allowed region. None of them are falling in the non-allowed region. That means they are stable and they can exist. Right? And in the figure B, then you can see that this is a Ramachandran plot of an enzyme pyruvate kinase from rabbit. So in this plot you can see that all of the so this pyruvate kinase, so they have plotted each of the amino acids of the pyruvate kinase in the Ramachandran plot, and we can see that each of the amino acids are falling within the allowed region, blue region. Only the glycine, which are in the not in the allowed region, they are in the non-allowed region. So glycines are falling in the non-allowed region, right? The phi-psi combination of glycine, they are falling in the non-allowed region, right? So now you can ask me that if all other amino acids are okay, but glycines are falling in non-allowed region, then how this enzyme is stable? Do you have this question?
Yes, sir.
So why do you think that others are fine, but only glycine is not falling? So how can it stabilizing the protein structure? Because glycine has no R group, so it is very flexible, so it can adjust anywhere. Okay, so because of this flexibility, as it does not have any R group, right? Because of that, glycine can, even if the glycine is um, falling in this non-alone region, the protein will be stable because glycine is very flexible. Now we will go to tertiary structure. Okay, so what is tertiary structure? As we saw in secondary structure, it is forming between the amino acids of a same molecule, intermolecular structure, right?
Yes.
Yeah. So as we know that from secondary structure definition that the amino acids are making interaction between each other, and we are getting secondary structure, right? Intermolecular interaction. Here, tertiary structure is secondary structures, multiple secondary structures will come and it will interact with each other and they will make the protein structure more compact, more complex. Right? That is called tertiary
Tertiary.
tertiary protein structure. Right? Secondary structures will come and they will interact with each other and they will make a uh, more complex, more compact protein structure. For example, in your hair, there is a protein called keratin, which has a tertiary structure. So what happens? This is the secondary structure of the keratin, alpha helix. Keratin has extended alpha helix, right? A series of alpha helix. So when these alpha helix are uh, interwound, when the alpha helix of are interwound in a left-handed sense to form two-chained coiled coils, right? When this alpha helix will interwound among itself, then it will make a two-chained coiled coil. Okay. Now multiple two-chained coiled coil will come and they will make a protofilament. The length will be 20 to 30 angstrom, and then multiple protofilament will come and they will assemble to make protofibril. Okay, right? So this is your tertiary structure of alpha of your hair keratin, right? So that's why your hair, the normal nature of hair is curliness because of this protofibril. Uh, okay, so because of this tertiary structure, the hair is curly. That's why when someone straighten their hair, they will apply heat. So in the heat, this tertiary structure will be denatured, right? So that's why the keratin will be uh, this tertiary structure will be denatured, so the hair will be straightened, right? So and as you know that hair is an array of alpha keratin filament. This protofibril, they are the alpha keratin filament, right? So this is an example of tertiary structure. Another example is collagen. Collagen has three alpha helix, right? That's why it is called as triple helix collagen. Also, it is made up of three alpha helix and it has the repeating tripeptide sequence glycine X proline. X can be any amino acid, so glycine X and proline, or glycine X and 4 HYP, right? So there are three parallel alpha helix will be there to form collagen. So here you can see that multiple three number of alpha helix, three secondary structures are coming and they are combining, they are getting assembled and they are making the tertiary structure of the collagen. That is tertiary structure. In keratin also you can see that multiple alpha helices will come, right? They are interrode and they are making a tertiary structure of the hair keratin, right? So these are the two examples of uh, tertiary structure of hair.
Tertiary structure. Yes, sir.
So now we
Sir,
will
can
see.
you continue tomorrow?
Huh?
Next class, can I continue?
Okay. Are you tired?
Actually, I don't have dinner.
Okay. Yeah. So actually, I have to finish it here in this meeting only. So if you have to go, you can go because I think this lecture will be uploaded. Okay, then you can see the remaining part.
Where it will be uploaded, sir?
That they will tell me. They will actually they will tell me.
Okay, we'll get any link and something.
Yeah. They will give some link, and anyway, I can
Ah,
send you guys the slides
this.
by
Yeah,
tonight.
yeah.
I will send you. Okay, then
Right.
let me complete this, and if you want to go, then okay, it's fine. You can see the recording.
It's already completed.
I mean,
How much time more you can take?
it will take 15 more minutes. Then it will be. If you
Okay.
have to go, you can go actually.
Actually, nothing. I am getting hungry. That's why. Yeah. It's okay.
No. It's fine. You can go, and later you can recheck with. You can again see it when the recordings will be available. Okay.
Okay. Thank you.
Okay, no problem. So these are the tertiary structure of protein. So next we will see the different protein, different motifs of protein. So so in motif, what is motif? The motif, the different secondary structure, more than one secondary structures will come, and they will assemble and combine, and then they will make you uh, motif, right? For example, beta alpha beta loop, where two beta sheets are connected by one alpha helix, right? That is called beta alpha beta loop. Alpha alpha corner, when two alpha helix come and they will make a motif of alpha alpha corner, right? These are the series of beta, all beta motif, right? This is a beta barrel, when multiple beta sheets will come and they will make a barrel like structure, right? So these are different motifs, and these are protein organization. So there are four kind of protein organization. One is all alpha. The proteins, these proteins, they have all alpha, right? So they have only one secondary structure, that is alpha helix, nothing else. All beta, they have only beta sheet as their secondary structure. They don't have alpha helix, right? Alpha slash beta means, and yeah, and the third category is alpha slash beta. These proteins has either alpha or beta. So this portion of the protein is made of beta sheet. This portion is made of alpha sheet. Here also, this portion is made of beta sheet and this portion is made of alpha helix. So they are alpha slash beta. It is called alpha plus beta. When the proteins has alpha as well as beta, then they are called alpha plus beta. So you can see here, alpha helix is there, beta sheet is also there, right? So they are together. So that is alpha plus beta. Okay. So any doubt you have till now? Okay. Aditya, your mic is not working. Sorry, I didn't see your text here. Okay, I can see your responses actually. Okay. Okay, probably you are having some network issue. So as your mic is not working, you can, yeah, mic issue is there. So do you have any doubt? You can ask me still here in the chat box. Yeah. Please ask me if you have doubt. Okay, so you don't have any problem, right? In the doubt. Okay, so I just wanted to know. So we are almost at the end of today's session. So we are almost at the end of today's session. So did you understood everything? And any feedback you want to give me so that I can improve in the from the next lectures? Any things you missed, you found, or anything? And I'm asking it to everyone if any feedback you want to give. Kuldeep and whoever is there. Actually, yeah, Kuldeep and Aditya. Okay, thank you. So, and just one thing to mention you guys that just if you are having facing any issue, you can also after this session also you can send me email or if you have any urgent doubt, you can uh, send me email for that. And in the next class also, actually you can ask me from the doubt of these classes. What are we going to learn in the next class? Did you see the flyer? I think it's available in the flyer. So probably we will wait. Let me just open the flyer. Yeah. So in the next class we will study about enzymes. Okay, Aditya. Yeah. Enzymes we will study in the next class. So just to wrap up today's session, I would like to inform you that yeah. So last week uh, studied the tertiary structure and this motifs of a protein and the domains all alpha alpha or beta and alpha plus beta, right? So these are the domains which are important for the protein function, right? These motifs are the motifs which they will form a domain of a protein, and each domain has some functional aspect for the proteins, right? In the enzymes chapter we will see the enzyme kinetics, as well as we will try to see some roles of this kind of protein domains, right? How does they do function? That we will also see in the enzyme lecture. Okay. Okay. So the next lecture is on tomorrow, Saturday, as you know. So I will again send you the email for the class, and the same meeting link will be used. Same meeting link, right? So the schedule will be self for each week. Friday and Saturday. I am writing in the chat. Friday 8 to 10 p.m. and Saturday 8 to 10 p.m. Okay, so each week it will be maintained Friday 8 to 9 p.m., Saturday 8 to 10 p.m. and the same meeting link will be used. So please join tomorrow at 8 p.m., 8 o'clock. Okay. 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 So I think we can end the session right now. So thank you everyone. Thanks for joining. We will meet you on tomorrow.